Hello everyone, I am Shikha Malhotra, going to be discussing about digital logic circuits, about combinational circuits and sequential circuits. So let's start with combinational circuits first. What are these? These circuits are circuits which contain different types of logic gates which are connected together. This circuit would have a combination of gates, and that's why they are called as combinational logic circuits. The output of this circuit is determined from the present combination of the inputs that are going into it, regardless of the previous input that went in. The input variables, the logic gates, and the output variables are the basic components of any combinational logic circuit. That is how the name suggests. The n binary input variables, which come from an external source, the m binary output variables that go to another external destination, and there's in between a connection of logic gates. That's how we define any combinational circuit. So three components: one, any number of input variables, any number of output variables, outputs, and a combination of gates which creates the n input variables and convert them into the m output variables. A few examples for these are an adder circuit, a subtractor circuit, a decoder, encoder, multiplexer and demultiplexer. So today we are going to take something which is a very commonly used circuit, and before we get there, let's see how these work. These are usually employed in any digital computers for generating a binary control decision and for providing the digital components which are required for data processing. Some of the characteristics of any combinational circuit is as follows. The output of a combinational circuit at any instant of time will depend only on the present input terminals. Please remember, it's completely dependent on the input that is going into the circuit. The combinational circuits do not use any memory. That's why we just said it uses only the input variables. The previous state of the input does not have any effect on the present state of the circuit. The combinational circuit can have n number of inputs and m number of outputs. Look at the block diagram here. We see you have A, B, C up to n as the inputs, which are going through a combination circuit, which is a basic combination of some logic gates which have been put together, and the outputs that we get here are A dash, B dash, C dash up to m. So as inputs ABC, outputs A dash, B dash and so on. Remember, we are not using any memory in this case. Let's look at the very first commonly used combinational circuit, which is a half adder. Now what does a half adder actually do? We know the computers perform a number of operations which are mathematical. So a most commonly used circuit would be a circuit which does a mathematical addition. So what we are doing here through this circuit is going to be a simple addition of two binary digits. That's what the basic function of a half adder is. Let's start understanding about it. The basic digital arithmetic circuit which is used for addition of two binary digits is called as a half adder circuit. This combinational circuit performs the arithmetic addition of only 2 bits, and that is why it is called half adder. It is designated to add two single bit binary numbers A and B. So this is a basic building block for addition of two single bit numbers. The circuit will have two outputs, one which is usually the sum because we are doing an addition here, and one can be a carry. So two inputs A and B, which are two single bit binary numbers, and output side we will have one sum and the other is carry. Let's look at this block diagram first. So A and B here are the inputs. We have two outputs. One is a sum, which is the function that actually a half adder is supposed to do, and in some cases you may have a carry. So keeping in mind that there are two inputs, look at the truth table now. You have two variables A and B, so 4 combinations. Output side we have a sum and we have a carry. Sum being represented by S, carry being represented by a C. So if we look at this truth table, we very clearly see that we are going to implement this circuit diagram. Let's look at the first equation that we get out of the sum is x dash y plus xy dash, because we have a 0, 1, 1, 0 in the column of sum. So I'm getting back there. S is x dash y plus xy dash. which can also be represented by an XOR gate, because that's the output an XOR gate gives us. Look at the carry column. So it has all three zeros and a 1 only in the case when both the inputs are 1, which is represented by XY, which is the actual output that an AND gate gives us. So just representing these two statements again for sum and carry through our circuit diagram, you have two inputs A and B going through an XOR gate which gives the output of a sum. The same inputs A and B going into an AND gate which gives us the output of carry. So the C output is 0 unless both inputs are 1. Look at the truth table again. So we just did this. All three outputs for carry is 0. Only the last one is a 1 because you have both the inputs A and B as a 1 each. The S output, which represents the least significant bit of the sum, because that's the carry that is going to be used here, we have this being represented by the AND gate. That is how a half adder circuit works. Now the only problem that a half adder has, that it's taking an input of 2 bits, which is not the normal scenario. In a day-to-day basis, we do not add only 2-bit numbers. We will have multiple bit numbers being added and multiple digits being added together. So the drawback of half adder is being developed, removed through another circuit which is called as a full adder. Now what is a full adder? The name itself suggests it is going to take care of the addition of any number of input bits. Because half adder was doing only for 2 bits, here we are going to have multiple bits addition possible through a full adder. So full adder is developed to overcome the drawback of a half adder circuit. It is a combinational circuit as well, which forms the arithmetic sum of 3 input bits. In this example that we are going to take, we are taking 3 input bits. It will consider 3 inputs and they are going to be 2 outputs. 2 1-bit numbers A and B, and the carry will be C. The 2 outputs that we will get out of it are being shown by the symbol S for sum and a capital C for carry. That's a normal mathematical addition. What happens in this case? As we do in an arithmetic operation, the carry is always included as an input to the next addition. The same function is being performed by a full adder also. So we start off with 2 inputs A and B. We perform the sum. In case there is a carry in this, that carry small c, as we see is represented here, is also included as another input into the next bit addition. And that's why in some cases we may have a third input as a carry, and in some cases we may not have. So the circuit here shows A and B as your inputs and another C in, which is the input, the third input, which is coming from the previous bit addition. The outputs that we will get will be a sum S and a carry C. So in some cases we will have 3 inputs A, B, C. So let's take 3 input truth table, which will have 8 possible inputs or 8 possible combinations for the input of A, B and C. Looking at the table, the output column is S, which is showing the sum, and C0 is the, or CO as the C output, is the final output that you get out of the carry table. Now putting these the output of the truth table into an equation, we will get something like this. But before we get there, let's see what is the truth table trying to show. It says that when all input bits are 0, the output is 0, which is very clearly visible from the very first row. When all 3 inputs are 0, both the outputs are also 0. The S output is equal to 1 when only one input is equal to 1. Let's look at this. So if you look at the second row, output of S is 1 because C in is 1. Again, the next row, output S is 1 because the input B is 1. Next row, the rows 2 rows after that, again S is 1 because A is 1. And the last one is all 3's are 1, so your sum is also 1. Or when all the 3 inputs are equal to 1, which is what I was reading from the truth table right now. The C output has a carry of 1 if 2 or 3 inputs are equal to 1. Let's look at this. The C has a carry 1, so look at the row number 4, carry O is 1 because you have 2 inputs B and C in as 1. Similarly, the row after that, you have again CO as 1 because you have A and C in as 1 each. The next row, Again, CO is 1 because A and B are 1 each. And last, of course, we just discussed that both for the sum as well as the carry output, it is 1 because all 3 inputs were 1. The C output has a carry of 1 if 2 or 3 inputs are equal to 1. This is what we just discussed. Now, trying to summarize this through the equations, we will get this kind of an expression. We have an xy plus within the brackets you have an x dash y plus xy dash z, which is common with the z. So if I replace this x dash y plus xy dash, I know this is a representation for an XOR. So you can write this as a simpler form. So we can convert the statement for sum as XOR y and y or XOR z, and the carry can be represented as xy plus xy XOR with a common of z. This kind of simplification we do so that the circuit diagram that we develop is a simpler form. To simplify these equations, we've actually used the first expression and created a truth table, a Carnot map out of this. So the very first K map, if you look at it, is for the sum expression where you have 4 inputs, x dash y dash z, x dash y z dash, x y dash z dash and x y z. All these 4 have been marked in the appropriate cells. But incidentally, since it is a table where we do not see, or it's a K map where we do not see any simplification happening because no grouping is happening, we just have the same thing as the output, which has been just represented by an XOR between x and y, and similarly an XOR between y and z. Looking at the carry expression, we had xy plus x dash y plus xy dash with a common of z. We just put this in the K map. Look at the possible groupings that we have. The groupings have simplified this expression, and we have the simplified expression available in front of us. Please remember, we use the K maps to simplify any Boolean expression that we are using so that our circuit diagram becomes simpler and with lesser number of gates. So if I had to put these expressions in this format without simplifying them, I would end up using more number of gates. After simplification through a K map, we know the expression that we get is the simplest possible expression, and hence we have a simplest circuit diagram that is available. Look at the very first one. It's an XOR gate which has 3 inputs A, B and C in, and the output is S. The next one is an AND with AB, then another one is AC in, and the third one is BC in. All these 3 individually inputs getting into each AND gate, and the output we get is the final C output gate, which is going through an OR gate. That's how, if you look at it, we have only 5 gates being used here in this circuit diagram, whereas if I had not simplified this, there would be multiple times more gates that would have been used to develop a full adder circuit. So the advantage of the K maps is to reduce the number of gates and to simplify your expression, which in turn simplifies the circuit diagram also. The next kind of circuit that we use here is a half subtractor. Now, the way the half adder does the addition of 2 binary numbers, similarly a half subtractor is a circuit which is used only for subtracting 2 binary numbers. Similar to the half adder, we will have a very simple input. You will have only 2 inputs and the output would be similar to that. One would be a difference and the other would be a borrow. In case of a half adder, we had a sum and a carry. In case of a half subtractor, we will have a difference and a borrow. So the circuit that is used to subtract 2 single bit binary numbers A and B, the difference and borrow are the 2 output states of the half subtractor. Again, going through the circuit diagram or maybe a block diagram first, the half subtractor circuit, you see 2 inputs A and B, 2 outputs. One is a normal difference that we do because it's a subtraction that we're going to do through this circuit. So like a mathematical expression, we will have a difference here, and in a normal arithmetic expression also we do borrow numbers, so we have a borrow output here in this case as well. Please remember, all this is being done on just parallel to your actual arithmetic expressions. So keep your arithmetic operations in mind and that is exactly what a half adder or a full adder or a half subtractor or further a full subtractor circuit will also be doing. Coming to the truth table, inputs are A and B, so we will have 4 possible combinations. Look at the difference column 0 1 1 0. Look at the borrow column 0 1 0 0. Let's see when is this going to happen in each of them. The difference and the borrow expressions from the truth table have been converted into the terms of the inputs A and B. So since we had 0 1 1 0 in the difference column, the expression will be written as A dash B plus AB dash. Look at the borrow, you have only a single 1 appearing in the second row, so we have the expression as A dash B. Look at the circuit, 2 inputs A and B going through an XOR giving us a difference operation. Similarly, just to convert that A into A dash, we have put an inverter there, and we have a A dash input and a B input going into an AND gate, so the output coming out as A dash B. This is the simplest form of an expression and a simple circuit being represented through this circuit. That's what a half subtractor does. Now similar to this, we also have drawbacks with this half subtractor circuit. What is this drawback? The drawback is that it is used only for 2 numbers. So what do we do in that case? We need to expand this half subtractor circuit into a bigger circuit which is capable of handling more than 2 units. The half subtractor is used to subtract only 2 numbers, whereas that's not what we do in our real life. We also have multiple other operations or multiple numbers being used for a subtraction operation. So to remove that drawback from a half subtractor circuit, we will have another circuit called as a full subtractor. So the full subtractor is used to subtract 3 1-bit numbers A, B and C, which are the minuend, subtrahend and the borrow. The full subtractor has 3 input states and 2 output states. Of course, these are going to be the difference and the borrow, as we've already seen them in the half subtractor circuit. Let's look at this full subtractor circuit now. 2 inputs A and B. Please compare this entire operation with a regular arithmetic subtraction operation. Sometimes we have to borrow the number from the next digit to be able to subtract this. So similarly, the third input that is going in here is the borrow in. This is in the case when we have to borrow from a previous digit to be able to subtract the number here. So that automatically starts getting counted as one more input. So that's the reason we are considering 2 inputs A and B and the borrow in as the third input. What's the output side? 2 outputs. One, the difference, that is what the operation is about. The other is the borrow out, which is going to be a part of your subtraction operation. So this makes it 3 inputs for a full subtractor circuit. So the truth table automatically has 8 inputs or 8 possible combinations for the input, 3 inputs converting into 8 possible combinations. Let's look at these inputs here. The input side has 3 columns, A, B and the borrow in from the previous one. The output would have 2 outputs. One is a difference, that is what we are trying to find out, and the other one is a borrow out. Let's look at the table and try and convert this into an expression. So in the SOP form, if I look at the difference column, we have ones appearing at 4 places. Row number 2, 3, 4 and the last row. The expression for that would be A dash, B dash and borrow in. This is what you see. So you have X, Y dash, Z dash, X dash, Y dash, Z, X, Y, Z and X dash, Y, Z dash. These are the 4 places where you are having a 1 appearing in your column for the output, for the difference side. Again, look at this truth table. If you try and simplify this, there is no grouping that is possible. So automatically this remains as it is, which means that there is no simplification happening in this difference K-map. Go back to the borrow now. So when we went back to the borrow, the expression that we got from there was x dash z, x dash y and yz. Map this onto your K-map, look at these values, and you can see there are three groups can be made to simplify the K-map. The simplification here gives us the output that we've actually seen up there. Because you could group a number of ones together as how the K-map tells you, you have been able to simplify this expression. Now what is it about? Why did we do this simplification? Was to create a circuit. If you look at this full subtractor circuit, I have represented it as half subtractor circuit A, another half subtractor circuit B, and then an OR gate and so on. Now this shows that when we start putting the difference statement and this expression for borrow, these terms can also be achieved as an output of the half subtractor circuit. So for this, let's get back to the circuit of the half subtractor, because that is where this was. This in the entire circuit of the half subtractor is what you need to imagine is actually present here as the half subtractor circuit A, because that is the input that is going as A and B. Now the output that we are getting out of it is going into the half subtractor B, and similarly is also going into your borrow from the gate, from the A circuit. Again, look at the half subtractor circuit B. There's a borrow in coming in and there's an input that is coming in from the first half subtractor circuit A. These two inputs will give us an output of the final difference, and the borrow B goes into the OR gate. Putting all this borrow B and borrow A into the OR gate, we actually get the final borrow out. So if you look at it, the difference is coming out immediately after the input has gone through half subtractor circuit A and half subtractor circuit B, whereas the final borrow out is coming after yet going through another OR gate. Now this is how a full subtractor can be expressed in terms of two half subtractors put together. So full subtractor doesn't really mean that it has to be two halves together, yet we have tried to show this, that if we try and represent a full subtractor circuit, the output could be got through even implementing two half subtractor circuits put together, and the output got in this format. So today we have discussed about four circuits, which are half adder circuit, a full adder circuit, a half subtractor circuit and a full subtractor circuit.